Oh, good morning, everyone. Can you guys hear me?
Yes.
Okay. So, I want to welcome you to my lecture today. Today, July 13, 2020. Uh, we actually going to continue on the logistic regression. Uh, I call this logistic regression part 4. Okay. We've done like 3 lectures on logistic regression, and this is going to be part of the lecture series on logistical regression. Okay, so that's going to be the focus of today. Today, I'm actually going to meet you for just 1 hour, just going to meet you briefly. Okay, so and after that, I'm actually going to talk about some other issues. I'm going to give you updates on the midterm and some other thing. Okay, so like I said, the focus is on logistic regression, and this is your part 4. So, which means this is the fourth in the series of lectures we have had on logistic. Okay. Can you guys see what I'm projecting right now? Yeah, can
Yes.
somebody confirm if you are seeing what I'm projecting right now? The
You
logistic
just did.
regression part 4. Okay, you did, right?
Yep.
Okay, thank you so much. Um, now, the example today will actually be on Sudoku game. I don't know. Has any one of you heard about Sudoku game? Sudoku game. Has anybody heard about that? Okay. Sudoku game is just a game that is played. Just like you know the combination of you put different kind of combination of letters together to make sense. Okay. So the data set that we actually use here is 138 students of star 3032. Okay, so this was actually conducted during the probably last year. Okay, where 300 and where 138 students of star 3032 actually completed a Sudoku game in class. And let me tell you, we got two sections. We got two sections of the course. Just like right now that we got start 3032 and start 5302 that are being kind of cross listed. But here we got two sections of 3032. You know, as far as this data set is concerned. Okay, so we got section 1 and section 5. Okay, now I wanted to take a look at the variables that we have right here. Okay, uh, there are different kind of Sudoku game. Okay, there are 3 of them. Okay, I'm going to give you the definition for each of that. Uh, Now take a look at that. Sudoku game in Greek letters, Sudoku game in English letters, Sudoku game in numbers, Sudoku game in symbols. Okay, so there are 4 games. There are 4 Sudoku game, and okay. So, but the one that I'm actually showing you right here is just for 6 data point. Okay, and don't forget that we actually considered 138 students. Okay, and this 138 students actually come from different section. Okay, of the course. Okay, 1111 is more or less like those from section 1. Okay, and 555, actually going to be those from section 5. Okay, and you know what? Uh, the numbers they are trying to put together is either at the end of the day, it's either they are correct or not. Okay, So that's actually going to be the response, what I have right here. Okay. Is that they put the combination of numbers or the combination of Greek letter, the combination of English letter, you know, putting them together. Of course, we actually want to see whether they're going to be correct in the formulation at the end of the day, and that's why you actually have 0 and 1. Okay, so it's categorical. Okay, and you know what I have right here is just like, okay, what is a number of time, how many seconds does it take a particular individual, you know to formulate, okay, so how many seconds, okay, so like the first person here is not available, but the second person here actually used 419 seconds, okay, to actually to work with the combination. That also talk about whether you know the player this time around has the knowledge of the game. Okay, those who are first timer in the game, those who haven't played that game Sudoku before, we're going to code them as 0, and those who have played Sudoku game before, we're actually going to code them as 1. Okay, so I just want to tell you that we got a lot of variables right here, ranging from predictor to the response. And of course, the predictor is just going to, the response is actually going to be the correctness, okay? And the predictors is going to be, okay, which section are you from? Uh, are those people from section 001 or section 005 able to have the correct formulation of the game or not? Okay, so that's why we're going to look at the effect of the section, okay, of the student on the correctness. Okay, we're also going to look at the effect of the completion time. Okay, what is the effect of completion time on the correctness? Okay, and then we're also going to investigate the impact of whether you have played the Sudoku game before or not, because some people may argue that with me, okay, that okay, those who have played Sudoku game before, they are more likely to, have it done in time, and they are more likely to have a correct formulation. Okay, so we're also going to test that, and then we're also going to test the effects of, different levels of game. Okay, so we're going to look at the effect of games on Sudoku game on the correctness as well. So these are the variables that we're going to have in our model. Okay, so based on the data that we have, uh, the number of cans for the Greek letters is 34, the English letter 34, the numbers 34, and symbols 36. Don't forget that this is talking about the Sudoku game. Okay, we got 4 different kind of Sudoku game. So it means 34 student actually attempted that one. Okay, and 34 for this, 34 for that, and 36 for that. And if we actually want to know the number of students that actually played all the games, probably from section 1, that's 61. Okay, from section 5 is 77. Okay, and you know what? We also have kind response. Okay, so the number of students that got the combination correctly is 106, and 32 of them actually, get it wrong. Okay, 32 of them got it wrong. Okay, so this is just exploring our data. Okay, after the game has been played. Okay, and looking at the completion time. Okay, we also have, this is the histogram. Okay, the that is showcasing the probability distribution of the probability distribution of the of the completion time. Okay, so that's exactly what you have right here. And don't forget, I told you, if you are actually want to do regression modeling, okay, you need to, for of us, have what I call descriptive statistics, just like what I'm doing right here. Okay, so what I'm trying to do right now, I'm actually trying to exploit. my data set. Okay, why do I need to exploit my data set? Because uh, because I really want to understand the nature of my data set. Okay, because it's just like data set to statisticians or data set to researcher is synonymous with relationship between the patient and the doctor. Okay, patient is more or less like a data set, and a doctor is more or less like a researcher, okay, the analyst. Okay, so if a doctor actually want to treat the patient, okay, uh adequately, if a doctor really want to succeed in making sure that, okay, he has already treated this patient, I think the doctor need to do what I call diagnosis. Okay, need to do a lot of diagnosis. You need to exploit in a way is trying to exploit the patient, just for him to be able to understand the nature of the ailment, and understanding the the nature of the ailment will actually go a long way, you know, in in the doctor, adequately treating the patient. And that's exactly what we are doing, what we normally want to do in statistics that we call preliminary investigation. Okay, so I need to first exploit my data set to be able to get what I'm having right now, trying to get a distribution of that, and from there I'm now going inferential. Okay, so after understanding my data set, now the next thing I'm actually going to do is actually to go inferential. And what do I mean going inferential? Going inferential is just that, okay, I think I need to identify what are the variables. I've shown you the variables of interest. The next thing I want to do, okay, so which variable is actually going to act as predictor, and which one is actually going to act as response, okay? Going by the goal of this research, okay, want to, we have identified which Sudoku game, the section you belong, the completion time, which is measured in seconds, and your knowledge of the game is would go a long way in predicting the correctness. Okay, so it means the correctness is actually going to be response. Okay, why these are the potential predictors. Okay. Before I move forward, is there anyone who want to ask question? Are you guys hearing me?
Yes.
Yes.
Okay, so will I be right if I say you guys are good, right? Are you guys good?
Yep.
Okay, thanks for that. Okay, so the next, since I have my data set right now, so I'm actually going to run my code in R, okay? And of course, uh, if I want to run my coding out, this is what I'm going to write. And why am I writing this is because, of course, the response variable is correctness. And of course, I actually need to use logistic regression, okay? Because the response variable is, it doesn't matter the nature of predictors, okay? But the fact that the response variable is categorical, okay, I'm actually going to use logistical regression because the correctness is just like, okay, you're going to have two nature. It's either you get it right or you get it wrong, okay? And that is what make it categorical. Okay, so in my model, in my code, I'm actually going to put GLM, of course, because logistic regression, of course, is a member of a generalized linear model. Okay, so the one here is just like indicating my intercept. Okay, the regressor for that. Okay, then I'm going to write. If you look at section, I'm going to factor that because I got two section. Okay, so here is the factor into section. Okay, so I think what I want to do right here, I actually want to start with a simple model. Okay, just I just only want to have one predictor for now. Okay, I actually want to measure the effects of section on the correctness of the game. Okay, that's exactly what I want to do. Okay, and I'm actually going to call that mode one. Okay, so this is the result that I have. So the way I want to start it, I don't want to use all the predictors at a time. I actually want to start by looking at the effect of one predictor at a time before I move to the complicated one. Okay, so if you take a look at what I have right here, some of you may actually want to ask, why do I need to apply the AS dot factor function here? Because I think I need to do that so that I will be able to measure the effect of, because I got two levels of that. Of course, I'm actually going to have one dummy, okay? One is actually going to be treated as a reference. Okay, so when you do the coding in R, okay, when you code something as 1 and you code something as 5, don't forget that the section here, we got section 1 and section 5. And then I think I actually coded section 1 as 1, okay, and section 5 as 5. Okay, so when I do that, the output that is gonna come out, you're actually gonna have section 5. Okay, so which means section 1 is actually being treated as a control. Okay, it's actually treated as a point of reference. Okay, so that is actually what you're gonna see. Okay, so these are the estimates. These are the corresponding standard error. Of course, these are the z-value. Okay, you remember the other time I said when you are working with the logistic regression model, you are not going to be talking about test t-value, where you want to tell the significance of a particular predictor in the model. Okay, so if you want to tell the significance of a particular regressor in the model, of course, when you are working with a linear regression model, you're actually going to use t-test. Okay, but in the case of logistic, that's why you're going to see a z-value. Okay, and when I have a z-value, of course, I'm actually going to have a probability associated with the z-value, so which is a p-value. Okay, and of course, I'm actually going to use that, to test the significance of that parameter. Okay, so based on what I have right here, so the question now is, how can I really interpret section 005? Okay, how can I interpret what I have right here? Okay, let me tell you something. Uh, for 5, okay, for 5, okay, we are actually referring to section 5, and for 1, we are actually referring to section 1. Okay, so what we're trying to say, since section 1 is actually being treated, because automatically the R software, we actually treat section 1 as a point of reference. Okay, because we got two levels, you're actually going to report one dummy. Okay, so what we're trying to say right here, if I actually want to interpret, let me first start with the intercept. Okay, how do I interpret the intercept? Let me tell you this. If you want to interpret the intercept, okay, in a logistic regression, in a situation where you also have a predictor that is categorical, okay, so your intercept will actually be interpreted with a respect to the section 1. That is, with the respect to the level that you refer to as control. Okay, so if I want to do that right now, I'm actually going to base my interpretation on that. And come to this. That was why I said, take a look at this guy right here. How do I interpret the intercept right now? I'm actually going to say the estimated log odds. Okay, the estimated log odds of completing the Sudoku correctly for students in section 001. Okay, student in section 001 is coded as 1. Okay, under the predictor variable. Okay, they call it predictor variable here. It's actually categorical because it's a section. We got two sections, section 1 and section 5. Okay, if I want to interpret the intercept, I'm actually going to base my interpretation on the control. Okay, the level that I'm using as a control. Okay, and that is the reason why I'm going to say the estimated log odds of completing the Sudoku correctly for students in section 001 is 0.7932. So this guy here actually apply to the other level of predictor that is not here. What you see here now is section 5. So the intercept we actually have to do with the section 1. Okay, and that was why I said that. Okay, can you see that now? So that is a way to estimate the log odd. Okay, if I now want to estimate the probability, you remember what I showed you the other time, the log odds. I showed you something that has to do with the odd ratio. I showed you something that has to do with the log odd, and I showed you something that has to do with the estimated probability model. Okay, now if you take a look at what I have right here, I'm actually going to say the estimated probability of completing the Sudoku correctly for student in section 005 is 0.6885. Now the question is, how do I get a 0.685? How do I get that? You know what I'm going to do right now? I'm actually going to use this guy, the intercept. Okay, I'm going to plug it into the model. Okay, so and then I'm going to compute this guy here, and when I compute this guy here, I'm actually going to have, so this is a corresponding probability of of getting a correctness, okay, for any student in section 001. Is there any one of you who need clarification on how we interpret the estimated log odd and the way we interpret the estimated probability? Is there anyone who need clarification? Okay, so this is a way. Okay, I think I have a chart, something coming. Let me see. Somebody can you explain why you use log? Oh, that's a very good question. You remember where in the case of logistic regression, logistic regression is a log transformation of a linear regression. Actually, remember that I walk you through that, and you know that why do we need to log? We actually need to log hard. Of course, you know what I mean by hard, right? The hard ratio is just like, oh, what is the probability of correctness? The ratio of probability of correctness to the probability of getting it wrong. Okay, that is going to be the hard ratio. Okay, now when I log that, then I'm talking about the log of odd ratio. I mean the log of odd. Okay, so and why do I need to log? We need to log because that if we made an attempt to model that variable, that response variable, using the linear regression model, you're actually going to get a value that is going to be out of the range of 0 to 1. Okay, so you remember we were doing a log transformation before, right? When I was walking you through assumption violation in a linear regression, I walk you through different kind of power transformation. Okay, so the linear regression model, the logistic regression model is a log transformation of a linear regression model. Okay, and that was the reason why we have to talk about log. Okay, so the log, so that is the essence of talking about log. Okay, and you know what? The log does not actually indicate the probability because the log of odd is expressed in the ratio of two different probability. So in this case of Sudoku game, the denominator is actually going to be the probability of getting it right, okay? And the denominator is actually going to be the probability of getting it wrong, okay? So I think, does that person really understand the way I explained that now? The person that asks the question in the chat. Okay, so let me check my chat now. The person say yes, thank you. Okay, thank you too for asking question. Okay, so based on what I have here right now, a question can be asked. Do you know I can give you something like this in exam? Okay, I can actually give you something like this in exam, maybe in a multiple choice exam, and then I say, okay, on average, which section did better in correctness? How am I going to know that? if I really want to, I choose section 005. Why? I choose section 005 because the estimate of parameter that I have here, it has to do with, it is explaining the contribution of section 005, and you know what? It is positive. Okay, now take a look at that. This is actually positive, and not only that, this is so high. Okay, it's actually higher than positive. Okay, so what you're going to see, if it is positive, then it means it's actually, I think I'm still going to explain that, or give you more information about that later. Okay. Um, Now, the next thing we want to do now is interpreting the coefficient of the dummy, okay? The coefficient of 0.80. How do I interpret this guy here? Oh, I think I told you the other time, you don't interpret this as the similar way you did in the linear regression. You don't do that when you want to interpret the slope. Okay, so what you need to do, I walk you through that the other time. You actually need to find the exponential raised to power beta. Then whatever you get, you subtract 1. You remember I told you the other time? I walk you through this on Friday. I mean, so on Thursday. Okay. Now, so what I'm going to do, you are not going to interpret what you have here, but you need to use that. You need to plug that into an expression right here. Expression is actually going to be exponential raised to power beta, okay, minus 1, okay? So when you take the exponential of 0.8007, so whatever you have, you're actually going to subtract 1 from that. And you know what? When you do that, you're actually going to have it 1.23. Okay, then you need to multiply that by 100, and that will give you 123%. Okay, so if I want to interpret that now, I'm going to say compare to student in section 001, because right now what I have right here is is a contribution of section 005. Okay, so I'm actually going to say compare to the student in section 001, the odds of completing the Sudoku correctly increases by 123%. Okay, increases by 123% for students in section 005 on average. Okay, so when you say increases by 123%, I want to ask a question right now. I want to ask a question right now, and I'm actually going to award an extra credit. Can somebody tell me, if I compute this guy here, okay, and if what I have is 100%, okay, if I have 100% instead of 123%, okay, can somebody actually tell me what is the meaning of that? How can you compare, student in section A, how can you compare the odds of completing Sudoku game correctly by student in section 001 and 005? Can somebody tell me now, if this happens to be 100%, what is going to happen? What do you think is actually going to happen? What are we talking about? Okay, let me put it in a very right perspective. I think I'm going to give you a clue right now. If a beta naught, if a beta 1 equal to 0, okay? If a beta 1 equal to 0, the exponential raised power 0 is going to be 1, right? The exponential raised power 0 is going to be 1, right? And when I subtract 1 from 1, what do I have? When I subtract 1 from 1, I'm actually going to get 0. Now, getting 0 will actually mean that students, the odds of completing Sudoku correctly in the 2 sections of the class, okay, in the 2 sections, they are the same. Okay, I want to tell you that the moment the beta 1 equal to 0, of course, the exponential raised to power 0 is going to be 1. Okay, The moment beta 1 equal to 0, the exponential response that will be equal to 1. And 1 minus 1 will be equal to 0. So 0 means there is no difference between the two classes in terms of the odds of completing the Sudoku game correctly. Okay, so I think you take a look at that right now. Okay, so another thing that I want to talk about, what variable affect the correctness? We have really talked about, we only focus on the section, but this time around in our model, we actually want to, consider, which of the Sudoku game. Okay, I've looked at the effect of I've looked at the effect of the section, the section of the class in which the student belonged. Okay, but right now, what I want to do, I want to extend the tentacle of analysis, okay, of my investigation to which Sudoku game as a predictor. Okay, and don't forget, we got 4 levels of which Sudoku game. Because of that, we're actually going to get 3 dummies. And the first Sudoku game, we're actually going to be treated as a point of reference. Okay, it's actually going to be treated as a point of reference. Okay, so and that is the reason why you are always seeing 3 right here. Okay, now this is the intercept for this model. Okay, and the intercept for this model right now, we only apply to, okay, I want to award an extra credit right now. Can somebody tell me that if I want to interpret the intercept in this model, that will have to do with what? Which of the Sudoku? Which of the Sudoku? Can somebody tell me? Which of the Sudoku game would that intercept apply to? Okay, so they said Sudoku 1. Good job. Okay, for those of you that said Sudoku 1, that's good. Okay, remind me to send a message to me for extra credits. And don't forget, I told you something about my extra credit before, that when you write your final exam, okay, after your final exam, you need to tell me the total number of extra credits you have earned in this course, and you also need to tell me how you want to spend it, okay? And that's going to be after my exam, after the final exam is reading. Okay, you are right. So it's going to be Sudoku 1, okay? Now, if you take a look at the p-value that I have right here, looking at the type of Sudoku game, as a potential predictor, you can see none of them is significant, right? Can you see that now? None of them is significant because the p-value associated with them is very, very large compared to the level of significance, okay? Now, and that was why we said none of the p-value is small enough to reject the non-hypothesis that the slope equal to 0, okay? You know that when the slope equal to 0, you're actually going to have intercept, right? You're actually going to have intercept, okay? When the slope is actually equal to 0, okay? So based on the estimated coefficient in the fitted model, or please disregard the large p-value for now, okay? We know that, the predictor here has actually failed a test of significance, but we don't want to deal with that for now. We want to disregard, this guy for now, because the essence of what we're trying to do right now is just that, okay, how can we tell about the contribution, okay? We're not care about whether the contribution is significant for now, okay? And that was why, so what we really want to do right now is just, okay, which Sudoku has the highest probability of correctness on average? Okay, now let me tell you something. If you take a look at what I have here, because the range of predictor should be from 0 to 1, okay? The range of predictor should be from 0 to 1. I'm referring to the categorical predictor, categorical, okay? Categorical predictor. Of course, when you take a look at, if you take a look at what I have there, the Sudoku 3 has a 0.9343. And if I take you back, what is Sudoku 3? I'm going to go back to that now. I'm going to show you the Sudoku 3. Yeah, Sudoku 3 is, Sudoku game in numbers. Okay? Sudoku game in numbers. Okay? So that is Sudoku 3. Okay? Okay, so I think you get that right now, right? Okay, so based on the estimated coefficient, we can order the Sudoku by log odd from the highest to the lowest. Of course, as you can see right here, the largest one is Sudoku 3. Okay, that is actually followed by Sudoku 4. Okay, and that was why I said Sudoku 3 is greater than Sudoku 4, is greater than Sudoku 2, and greater than Sudoku 1. Okay, the Sudoku that you put under reference is going to be the least, the one that you put under reference. Okay, and that's actually going to be the least. And of course, we're actually going to be assuming this value for that. Okay, so that's exactly what you see here. Okay, so can you see that now? Okay, so we order that based on the estimated coefficient. Okay, we order that based on the estimated coefficient. Okay, now the next thing that we want to do, we want to test is, okay, which variable affects the correctness. This time around, we actually want to use a different predictor, and this time around, we actually want to test the knowledge of the game. Okay, we want to see the contribution of having knowledge of Sudoku game. Does that really impact the probability of correctness? And that's exactly what we want to test right here. But let me tell you something. Even before going into this research, okay, before going into this research, we got expectation that, of course, if you have the knowledge of Sudoku game, you are likely to do it very well. You are likely to come out with a very kind of a suitable combination, that will be adequate. Okay, we are likely, the probability of correctness can actually be maximized when you have the knowledge of the game. Okay, so we know this from theoretical perspective. Okay, now we actually want to test that right now, and this is the model, and take a look at that. It's highly significant. Okay, highly significant, compared to the other one that we did before that they were not significant. So this is highly significant. Okay, having the knowledge of the game before. Okay, but you know what, if you look at this, we did not apply factor here. We didn't factor that. Okay, we just modeled that as a quantitative variable. Okay, we didn't factor that. Okay, and that was the reason why you can see 1.6452. This is not a range, compared to the one that was factored. Okay, the one that was factored, I think you can see that right now. Okay, you can see that right now. And if I take you to the other one, if I take you all the way up, I factored that one as well. You can see that you're actually going to have that in the range of 0 to 1. But if you don't factor a particular predictor, of course, you're actually going to, you can have any number. Okay, so the number you have here now is 1.6452. Okay, so we didn't factor that. Okay, we are trying to measure, and if you take a look at the data for before, I'm going to show you right now. You're actually going to see the nature of the data for that. Okay, take a look at it right here. It's categorical. Can you see that now? It's categorical. It's on 0 and 1. Okay, so when a predictor is on 0 and 1, you may not necessarily need to factor that. Okay, but if you take a look at what I have right here, if you take a look at what I have right here, I did not code that as 0 and 1. I coded that as 1 and 5. Okay, why do I have to code that as 1 and 5? Because the 1 is indicating section 1, section 001, and 5 is indicating section 005. Okay, now based on what we have right now, based on what we have, I'm gonna take you to where. Give me 1 second. Okay, so based on what we have right now, the question now is how, or based on the fitted model, does experience improve the probability of correctness? Of course, the answer is yes. Yes, because the experience is categorized as before, or there are those who have the knowledge of the game, and those who do not have the knowledge of the game. Okay, so those who have the knowledge of the game, you can see what you have right here, and it is highly significant. And that was okay, yes. And how can we interpret? Of course, look at that. It's positive, because positive means having the knowledge of that is positively related to the correctness. Okay, it's positively related. It means it actually have a positive contribution to the correctness. And you can see that now. So if I now want to interpret that now, I'm actually going to say the estimated log odd of correctness for students with Sudoku experience is higher than that of student without Sudoku experience, because what is actually showing you right here is the estimated coefficient for those with the Sudoku experience, those who have played the game before. Okay, so and that was why we said the estimated log odd of correctness for the student with Sudoku experience is higher than that of the student without Sudoku experience. Now, let me tell you this. What we're talking about is just at the log of the odd ratio. What do I have in the ratio? What I have in the ratio is what I have at the top. What I have as a numerator is actually going to be experience, those who have the knowledge of it before, divided by those who do not have the knowledge. And that's exactly what I'm trying to talk about right here. The ratio of that, the log odd, the log of the ratio, okay? The log of the ratio, the estimated log of the ratio of those who have played the game before divided by those who have not played the game before. And of course, when the log of odd ratio is greater than 1, look at that. So this is 1.6452, okay? So definitely, those who have experience, of course, the estimated log of correctness will actually be higher than those who do not have the experience. Okay, so then we can also talk about, and that will also implies the same for the probability, because they're actually going to go together. Okay, they're going to go together. Okay. Because if I want to find the probability, I can actually use the function right here, because I know the log odds, okay? The log odd is equal to the ratio of the probability of correctness divided by the probability of, of getting it wrong. Okay, when I solve that. So what I'm trying to say in essence is that the estimated probability of correctness for the students with Sudoku experience is higher than that of student without Sudoku experience. Of course, that's exactly what we have. That's what we're going to have, because the estimated probability we actually go with the decision that we took, with the log odd of correctness. Okay, so another thing I want to measure right now, can I actually measure the effect of completion time on the correctness? That's exactly what I want to do right here. The completion time, okay? The time it takes for you to be done with your formulation, how does that time, how does it affect correctness? Okay? Some people may actually argue it out that those who will finish on time maybe are probably those who have the knowledge of the game or something like that. But let's critically study correctness right now. Okay, I mean, let's study the effect of completion time on correctness right now. And that's exactly what we're doing right here. And it's actually significant. Okay, and don't forget my predictor right here is quantitative in nature. Okay, it's quantitative, it's not categorical. Okay, and you know what, since it is not categorical, actually the estimate of that is negative. Okay, the estimate of that is negative. Okay, so we can actually interpret that as follows. So based on the fitted model, okay, is completion time associated with the correctness? And the answer is yes. How do I know? They are related. They are related because you look at that, this is highly significant. Can you see that now? It's significant. So I'm going to say yes. Then I'm going to say the completion time has a negative association with correctness. This is it. Can you see that now? That's a negative one. Now, if something has a negative relationship with something, what do we mean by that? In the actual sense, what I'm talking about is just that, you know, for every unit increase, when the time goes down, okay, that will lead to high correctness. So which may justify the fact that the moment I quickly complete my game on time, it means maybe I get the knowledge of the game, most of it. Maybe that was the reason why I'm able to, to do that on time. Okay. But you know what? One of your classmates raised an excellent question, said the small p-value, which is right here, indicates that the slope of second is significantly different from zero. How come that the estimated slope, which is this guy here, is so close to zero? If you take a look at what I have here, okay, despite the fact that this is statistically significant, but when you look at this value here, it's very close to zero. Let me remind you of what we have done before. If you really want to tell the significance of beta 1, you know how we normally do that. We set up an hypothesis, right? We got the non-hypothesis, we got the alternative, right? Under the non-hypothesis, we're going to say, oh, okay, beta 1 equal to 0. And under the alternative, we're going to say beta 1 not equal to 0. But take a look at the estimate right here. It's very close to 0. But you know what? It is significant, because this is trying to tell us it is significantly different from 0. That's what it's trying to say. But you know what? Merely looking at this value right here, it's not far from 0. Okay. Okay. Now I'm going to tell you why. Now the estimated slope, okay, represent the effect size. Okay. That is the amount of increase in the log odds by 1 second increase in completion time. Okay. When there's a unit increase in completion time, okay, so the amount of increase in log odd, okay, that is what actually represent. Okay, when there's an when the second increase by 1, when the completion time increase by 1 unit, the log odds. I needed to say the log odds. Whatever you see in the output of a regression model, of a logistic regression model, we normally refer to that, particularly when we are talking about, the estimate right here, we used to refer to the log odds. Okay. And that was why we said the estimated slope, that is this guy, represent the effect size, and which is the amount of increase in the log odds by 1 second increase in completion time. Okay. And you know what? The p-value measures how strongly the data support the slope being non-zero. I think you know that, because when you have a small p-value, you are actually going to reject the non-hypothesis and conclude that beta 1 is significantly different from 0. Okay, so they are measuring two different things. Okay, they are actually measuring two different things. So we can have an effect size close to zero, just like this. Okay, we can have an effect size close to zero, just like that. Y being significantly different from zero. You can see that. Okay, it doesn't really matter. Okay, what really matters a lot to us is what is the associated p-value for that. Okay, and of course, we get a p-value based on the z-value. Okay, and the z-value is the ratio of the estimate to the standard error. Okay, now we have been trying to look at the effects of each predictor in the model, in relation to the response variable called correctness. But what we actually want to do right now, we actually want to use all the predictors, in the model. Okay, take a look at that. We want to use section. We want to talk about before the experience in the game. We want to talk about the kind of Sudoku game. Okay, and we want to talk about the impact of completion time. Okay, we're doing all this at the same time, and this make it a complicated model. Okay, and this is the result that we have. Okay, I want you to take a look at this result right now. Before is significant, right? And seconds in the completion time is significant. And you know what? When we're doing that separately, let's see, when we're trying to investigate that, you can see that now, time, completion time, significant. What about the experience in the game? Let's go to the experience in the game. Look at that. That's also significant. And you know what? When we do it now, in the presence of other predictors, they are also significant. Can you see that now? Okay. So having this now, that we can actually, take some notice. Okay. Now, after controlling, because the one we did before on a simple model, we did not control other predictors when we are working on a particular predictor. Okay. But having all of them in a model like this, of course, we are actually trying to tell the world we're actually going to control. Okay. So after controlling for student section, okay, Sudoku experience and completion time, okay, I'm actually telling you now how you can interpret, parameter, okay, the estimate of parameter in a model like this. So take a look at that. It now depends on what I want to talk about, okay. So I said after controlling for the student section, Sudoku experience and completion time, the log odds of correctness for the different Sudokus are ordered differently. Okay, so ordered differently. What are we talking about being ordered differently? Take a look at what I have here. I want to talk about the Sudoku game right now. We're talking about Sudoku game. Take a look at what I have here. What is going to be the largest one is actually going to be Sudoku game 2, right? And that was why I wrote Sudoku game 2, okay? That is English letters, okay? And that is going to be followed by 0.52, okay? And that is going to be followed by 0.3 something, which is Sudoku 3. And of course, the last one automatically becomes Sudoku 1, okay? I think you know that. That's going to be the last one. But you know what? The intercept right here does not imply that does not mean Sudoku 1, because we have other predictors in this model. This is going to be a general intercept, okay? And this is going to be a situation where we're talking about a zero level of all of that, okay? So we're going to write this one, okay? Can you see that now? Okay, so here is the order based on the model that only uses which Sudoku as the predictor on page 6, okay? If you look at what we have done before, I'm going to take you back. I think when I was working with the Sudoku as only predictor in the model, I'm going to show you right now. Take a look at that. This is what I'm talking about. This was the order before, okay? This was the order before. And I told you in this particular model right here, the intercept here is automatically talking about Sudoku 1. okay, which is this guy here, okay? So now, but in the case of the other one, it's not referring to Sudoku 1 because we also have other predictors that are categorical in this particular expression, okay? So what I have here right now is based on this output, and what I have here right now is based on the fact that when the student section, the Sudoku experience, and the completion time have not been controlled. That is why you have this arrangement. But you got this arrangement when they have been controlled. Okay, does that make sense to everyone now? Okay, so the next thing, after putting the model in place, and if everything is good, okay, the essence of building a logistic regression model is actually to come out with a model that we can actually use in making prediction. And let me tell you something that in logistic, we use logistic regression for classification. I'm going to say that again. We use logistic regression for classification. Classification in the sense that if I have a new data set, okay, if I have a new data, okay, where I have the knowledge of the student, okay, oh, this student is actually coming from section 1, and before you go to 0, oh, this particular student has not played Sudoku game before, okay, and this particular student actually played game 3, okay, and this particular student actually used 120 seconds as a completion time. Do you know that I can actually use the model to predict the estimated log of its correctness? Okay, I'm trying to talk about using the combination of, the model that I actually derived from the estimate of the parameters right here. Okay, give me one second. I want to put something in. Okay, so thanks for that. Okay, so like I said, do you know we can actually predict, okay, a new data, okay? If I have a new data, I have somebody coming from section 1, and this guy he doesn't have the knowledge of the game, and then he actually played a Sudoku game 3, and he actually completed the game in 120 seconds. Did you know that we can actually predict the estimated log of correctness? Okay, and not only that, we can also predict the estimated probability of correctness. Okay, so you can see the estimated log of correctness is not necessarily the same as the estimated probability of correctness. I think you can see that now. So this is the data set, collected based on a new individual that is not actually in the cohort of the data set that I use in fitting the model. Okay, so do you guys have any question? Because this is going to be the end of my lecture today. Is there anyone who have a trouble time who need clarification? Is there anyone? Before I go into general thing, is there anyone? Okay, so I want to thank. Okay, let me check my chat. Somebody said, "What does the type mean here?" Oh, let me see. Type. Oh, the type is just talking about the response. Okay, the type is the response. Okay, that's a very good question. Okay, if you really want to make prediction. Okay, if you want to make prediction, if you want to predict the estimated log of all, you're under the type, you're gonna put link. okay? But under, if you want to predict the probability of correctness under the type, you're actually going to put response, okay? Because why am I putting response? Because I actually want to figure out the probability of the characteristics of interest. What is the characteristics of interest? Then I'm referring to the correctness, and correctness is the response, okay? Okay, so that is what I'm talking about. But if you want to talk about, predicting the estimated log, then we are going to use a link, we're going to call link, okay? So that is why. So have I answered your question now? Somebody who, okay, so let me check. Okay, the person said, okay, I see. Okay. I want to thank everyone for attending my lecture today. I hope you guys are enjoying it. I want to tell you tomorrow we're going to do we're going to continue. It's going to be we're going to continue the logistic regression because we're going to have part 5. And let me